So Newton's second law is arguably the most important law that we will be learning this year. It is one of the most fundamental and key laws of physics. To introduce it, I thought we'd start with just a little example. So let's say you have a bug that has a mass of 5 grams. Here's the little bug. It's got wings. There we go. Antennae. There we go. And he hits a giant truck with a mass of 1,000 kilograms. So here's our giant truck. It's not exactly to scale. Here's the windshield of that truck. Which force would be bigger? Would the force that the bug exerts on the truck be bigger? Would the force that the truck exerts on the bug be bigger? Or would those two forces be the same? Take a second to think about it. Hopefully, you're remembering Newton's third law. Newton's third law is that for every action force, there's an equal and opposite reaction force. So that means that the force that the truck exerts on the bug has to be exactly the same magnitude as the force that the bug exerts backwards on the truck. So those two forces should be the same size. But that should leave you feeling like something is weird here. Like surely the bug feels a bigger force, like the bug is going to get flattened. The truck will barely even notice that it got hit by a bug. So how could these two forces be the same? And that is where Newton's second law becomes crucial to understand this. So Newton's second law is the idea that the sum of all the forces that act on an object is equal to that object's mass multiplied by that object's own acceleration. So mathematically, it looks like this. The net force on an object is equal to the object's mass times its acceleration. But practically, we actually don't use this law in this form very often. We almost always are splitting it up into x components and y components. So we'll be looking at the net force in the x direction on an object. That will equal the object's mass times its acceleration just in the x direction. And the net force in the y direction, the vertical direction on an object, will be equal to the object's mass again, times its acceleration just in the y direction. So that's how we practically use Newton's second law. So what does that have to do with our bug and truck example? Well, let's say we do the free body diagram of the bug. So here's the little bug getting hit by the truck. And when the bug gets hit by the truck, it feels a force from the truck like this. There's the force from the truck on the bug. So FTB meaning truck on bug. There's also going to be like maybe a little bit of a gravity force, maybe some like air lifting force from the bug flapping its little bug wings or whatever. But the main force that this bug will be feeling is the force in the truck, right? That's the most significant force here. So if I look at the net force on the bug, and specifically I'm looking at just the forces on the bug, right? Not forces the bug exerts on anyone else. That will equal the mass of the bug multiplied by the acceleration of the bug. That's a U. There we go. The thing is, though, this force is going to be a pretty decent sized force. It's from a truck hitting this bug. But the mass of the bug is going to be very, very small. So if I rearrange this for the acceleration and divide both sides by the mass of the bug, divide by the mass of the bug here, the acceleration is that net force divided by the mass. So if this mass is very small, and it is for the bug, right? So this is very small mass, then we're going to be dividing by a very small number. And that is going to lead to a very large acceleration. So if you take a force, just a regular average sized force, and divide by a tiny number, a tiny, tiny mass, you're going to get a huge acceleration here. So the bug will feel a large acceleration. So because the mass is small, the acceleration is very large for the bug. All right, I'm going to clear up some space here for me to draw a free body diagram of the truck and compare that. Doo-doo-doo. All right, so our truck here. So here's the truck. The truck feels a force from the bug, which is exactly the same size. So this is the force from the bug on the truck. It's exactly the same magnitude as the force from that the truck exerts on the bug. Now the truck will also feel all kinds of other forces. You know, gravity will be quite significant, the normal force. There's going to be some friction forces in there. Those will all be there as well. But just looking at the force from the bug on the truck and how that impacts the truck. If I know the net force on the truck is going to be equal to the mass of the truck times the acceleration of the truck, it's like a little tease here, meaning truck. And I rearrange that for acceleration again, divide both sides by mass. Then here I can see that if I take the net force on the truck, which is impacted a little tiny bit, right, by the force from the bug, that will impact the net force. But then I divide by the mass of the truck. Well, that's going to give me a tiny, tiny acceleration. So this medium-sized force from the bug on the truck divided by a huge mass, because the truck has a mass of 1,000 kilograms, gives you a very small acceleration. So here, because the mass of the truck is large, the acceleration of the truck is very small. So in terms of the motion of the truck, which is its acceleration, what the acceleration impacts, you're going to see very, very little impact from the bug, even though the force that the bug exerts on the truck is the same as the force that the truck exerted on the bug in the first place.